we got the streaming going. Are there any questions from last time? No questions from last time? All right. I got your email, so I'm going to open up the assignments. All right. So are there any questions related to the exam on next Tuesday? First question is, what exam? Are we having an exam? Yes, we are. On next Tuesday. Yeah. Yes.
In the last class, on example 1,
Uh-huh.
on the practice test,
Yes.
after line 188, where do you go?
Okay, so let's bring that back up again and then we can talk about it. I'm not sure whether this Zerno has it or not. This is from a different class, so no, not here. Recent documents. Do we have the other one? Let's see. Probably not. Okay, that's okay. We'll go ahead and find it. All right, so the first thing we need to do is to locate the exam first. So we will go to the shared folder, and inside the shared folder we'll look for 1189 x1 blah blah blah. Okay, so this is the one that we are talking about, and we'll just go ahead and open it from the browser. I think that works. Yeah, there we go. And you mentioned question number 1.
Yeah.
And the question is,
Once you get to line 188,
uh-huh.
you go to line 190.
Okay, so the question is, what happens when we are done, or what happens when we are immediately done with line 188? Is that the question?
Yeah.
Okay. So line 188 is a part of what? It's a part of the conditional statement. And the conditional statement is from which line to which line? It goes from 187 to 191. Okay. So when the then portion of a conditional statement is done, what do we do? Are we done with the entire conditional statement, or do we go to the else part? We're done with the entire conditional statement. So that means after line 188, we would be looking for a statement right after 191. Do we have a statement right after line 191? We do not. Okay? So that means when line 188 is done, we are done with whatever the loop needs to do. So what do we do after we are done with the body of a while loop? Well, it's called a loop because we have to go back, right? But the question is, where do we go back to? We go back to 186, which is asking the question of, is x different from 39? If true, we perform another iteration. If false, we get out of the loop. And in this case, there are no statements after the loop, so we get to post. So is that answering your question?
Yeah, I think so.
Okay. So the alternative to answer this question is to draw a picture. Okay. So I'm going to do it for this question, but you probably want to do it to the questions that you are asked on next Tuesday, if you want to understand, okay, how does this fit in the other thing, okay? Because I think that really is the question, is how does it fit? So to do that, I'm going to re-download this file first, and then we'll use Zerno to open it. Let me see if I can do this. Can I specify Zerno? So I don't need to, yep, there we go. Select and open. And once again, it probably has it open in some other window like there. So we'll put it over here. There we go. And zoom in just a little bit. All right. So what I'm going to do is I'm just going to draw the picture representing the same logic, but in a trail map fashion. Okay. All right. So we start with x gets 7, Now Xcode 7 is on its own. It is not a part of any larger structure. So it is just basically, its own little thing to do, okay? And it's only done once. It is not a part of the loop. Then we have a while loop. So we draw the overall construct of a while loop first, okay? So this is how we branch out. This is specifying the action inside the body of the loop. We'll leave ourselves a little bit of room because we have to draw something that's a little bit big in the inside, and then it loops back. And let me just double check, make sure the recorder is on. I'm pretty sure it is, but I forgot to turn it on for an earlier class today, so I'm just kind of mindful of that. So yes, the recorder is on. We are, recording the whatever it is we're talking about now. So the question we are asking here is, x is not 39. Okay. If it is true, we take this branch. If it is false, we take that branch. Are we good so far? So what I have drawn so far would be line 185, right? Because 185 is right here. Line 186 is kind of hard to pinpoint because line 186 is kind of specifying this portion here. So if I want to draw, or if I want to qualify one particular place of the trail map as line 186, that's kind of where I would pick. Okay, it's right before the branch, right before we have to make a decision. Are we going for another iteration, or are we getting out of the loop? Okay, is that okay so far? Okay, so the end of the loop is kind of hard to say. There's no line, or there's nothing to represent 182, 192, because there are two candidates that both make sense. Okay. I can put 192 here to basically say, this is the end of what we have to do repetitively, okay? I can also put it here to say that this is where we continue after the loop. So it's kind of ambiguous, and that's why we do not even put that label into this picture, because it's kind of ambiguous. I don't want to cause any type of ambiguation or confusion. All right, so now we have to draw a conditional statement, right? Because inside the loop is a conditional statement. So when you look at a conditional statement, which is from line 187 to line 191, you can kind of look at it independently, okay? You don't even have to know that it is in a loop, okay? So let me show you what I can do with the conditional statement. So I'm going to just draw the conditional statement as if it is a completely independent thing, okay? So every conditional statement has two branches. And to decide which branch we're going to go, we ask the question, is x less than 39? Okay. And if it is, we do this part. If it is not, we do this part here. And after each branch, we get out of the whole thing. Okay. Are we doing okay so far with the conditional statement picture? Okay. So now the question is, okay, what do we do for the true branch and the false branch? So this part here, I know it's getting hard to fit everything in here. X get x plus 17 is over this side, and then x gets x minus 1 is on this side. Is that okay? Okay. So now we have a pictorial representation of just the conditional statement from line 187 to line 191. But this is not the whole picture, is it? Okay, because we have this blank space here, in the for loop, and then we have this conditional statement that is kind of like floating in outer space, right? So what do? Copy and paste. And I'm not sure whether I have that tool. I think I do. I think this is the tool I want. I guess we'll find out when we do it, right? So we will cut and paste. Oh, okay, that's print. What about paste? Control V is paste. And then we'll carefully put it into here. Done. Does that make sense? So you draw a picture of a loop by itself, okay? You don't care what is inside the body of the loop. You just draw the outline of a loop. You have to specify the right condition, for instance, but you don't have to draw what is inside. Then you look into the inside of a loop and you say, okay, what is that going to look like? You draw that independently as if it is not inside the loop. When you're done drawing that thing, copy or cut and paste. Then you have the actual picture of the entire thing. Is that kind of answering your question? Okay. So if you really want this to look nicer, you can basically have this incoming path to connect to this path here, and have this outgoing path to connect here, and then just remove the square so that it looks as if it is a consistent map and you're not having a map inside a map. Okay? But the idea is it is a nested control structure, so it really is relevant and appropriate to look at it is a map inside a larger map. Is that okay? So if this is the case, does that explain why after line 188, we go back to line 186? This is line 188. When you're done with this, where do we go? We get out of the conditional statement, but there's nothing else after the conditional statement to do. Then we get out of the body of the loop, and that will take us all the way back to line 186, where we ask the question, is it true or false that x is different from 39? And then from that point, we kind of make a decision and proceed. Is that okay? Good? Yep, go ahead.
So if it is false, you just go to post?
If it is false, we go to post, because post in this entire picture is right here. Okay, the exit point of the entire thing is the post of the whole program, and you can look at this as pre. Is that okay? So it's okay to draw pictures, for the first few, algorithms that we encounter, but by the middle of the semester, we really should be able to understand the logic in pseudocode without having to draw a picture. Because the pictorial approach is great when you are dealing with an algorithm with relatively simple logic, but when the logic gets complicated, drawing this picture is going to take a lot of time. And and that's not how programs should be understood at a higher level. So the picture is only here to help us, to get the idea, get the concepts through. But once we understand the concepts, we should stop relying on pictures. Are we doing okay with this question? Any other questions related to the exam? Yes. It would include everything except for, in terms of the modules. So let me go back to the web page here. So go back a few times because I need to get back to Canvas. So it's going to include everything excluding pre and post condition, excluding the module called pre and post conditions. So none of the substitution, forget, inverse function stuff is going to be within the scope of the first exam. Is that okay? Does that answer the question? Yeah. Yes. Okay, very good. So we do include nested control structure in exam 1. Okay. So what I just described is 100% relevant to exam 1. Okay. Any other questions? No other questions? All right. So I'm still working on, trying to give you guys an assignment to work on pre and post conditions, but I don't want it to be too open-ended because, in the past, if I make it too open-ended, people easily lose track of, what is going on. So I'm still trying to design a homework assignment in the format so that people can follow that and step by step, and it is actually useful to help people understand what is going on. So I'm working on it. You will get an assignment on pre and post conditions, just not yet, okay? So what we'll do today, we're basically done with pre and post conditions, okay? So we're gonna move on to top-down design. Top-down design is related to the whole thing about nested control structure. So let me see, where is that open? It's one of these two. There we go, top-down design. Okay. So when we talk about top-down design, it's nothing new. You have been using this approach to do things in many of your other classes. How many people have taken English Writing 300? Okay, I would say at least about half the class. Okay, so what is the length of the last paper that you have to turn in that class in terms of pages or number of words? Does anyone want to tell me? Just approximately. I don't need to know the exact number.
1,000 words.
Huh?
1,000 words.
1,000?
No, it's actually like more than that.
I think it's like 600.
It was like around 2,500.
2,500 words. Okay. So we are talking about an article or a document that is 2,500 words, and it has to be meaningful, right? You cannot just repeat the same sentence over and over again until you get to 2,500 words. Okay. How do you get started with that process? Do you just kind of sit down and go like, okay, I'm starting here and I'll give myself 2 hours and then I'll be done. I'll just keep typing forward and get the 2,500 word assignment done. Is that how you do it? How did you do it?
We start with the context, talk about the background with an introduction and a summary.
So what you just told me, the background, introduction, summary, and the content, that's kind of, it sounds like an outline, right? So we started with an outline of what are the major pieces that we want to include in the paper, and then we go into one of those, right? Let's say we get into background first, okay? So do you just kind of sit down and just type out the entire background?
No, you start, when you do your outline,
Mm-hmm.
you're pretty much going to have like main points. You're going to start talking about these main points in each of the paragraphs.
I like that idea. You start with main points, okay? So if some points are main, what do you think the other points are? Not so main. They're minor or maybe details, right? So to support the main points. So in other words, you don't just kind of sit down and start typing, and then, after 2 hours you get your paper done. Okay? I'm pretty sure some people try that and failed. Because why do you think that's going to fail? If you are given an assignment, 2,500 words, and and on a particular topic to argue about something too, right? It's very simple. It's not like tell me about yourself from birth. I think most people can probably type that 2,500 words like without a break. Yep, go ahead.
It's not going to be focused.
Sorry?
It's not going to be focused.
It's not going to be focused. Why do you think that is the case? If we do not structure, if we do not break it down first, why do you think it's not going to be structured? It goes back to an earlier point that I have made already. It has to do with our short-term memory, right? I think we talked about this. What is the number, the typical number of things we can track mentally in our short-term memory? 5 to 9, okay? We did a Google search, and most people agree that it is between 500 words. Probably a little bit more than that, right? So what do we do now? We can only focus on 5 to 9 things. Let's say 5, okay? We can only focus on 5 things at the same time. But we have like a bazillion things to talk about in a 2,500 word paper. So what do? We start with the main points, okay? We start with an outline. The outline has 5 items. Can we track those 5 items? Here's the introduction, background, the actual body of the argument of some kind, a summary. That's less than 5. Yes, right? So you look at the background, or you look at the introduction. You break that down in return into about 5 points, 5 main points, okay? But I got a lot of things to talk about, okay? I look at all the little gibberish, scratch work, all the things I want to put into the introduction, and there are 20 things. Well, organize those into 5 main points, okay? Then you look at one main point of the introduction. What do? You say, well, can I list only up to 5 things, in here? So you keep breaking things down, and at each level, only up to 5 items, until it gets down to the point where, oh, I can write these 5 items in sentences. I don't have to use this approach to break it down into smaller concepts anymore. Does that make sense? Okay. if you want a more visual, kind of representation of what I just talked about, the easiest thing you can do is to look at Google Maps. Okay. Okay. This is actually pretty bad already. I mean, there are a lot of street names and locations on the map already, but nonetheless, it is still a lot better compared to having every single street spelled out and every single street address, okay, every street number, on the streets. Okay, it's still kind of messy, but not quite as bad as the alternative. So what happens when you zoom out? If I look at the whole map of Sacramento, do you think I can find details like where's Del Campo High School? Well, let's try it, right? So zoom out, and we are now looking at the Sacramento area. Oh, we cannot see Del Campo High School anymore. But the number of items on this map is still barely manageable. I can still kind of glance through it and go like, okay, where's Rosemont? I can see it over here. Takes a little bit of time if you're not familiar with where it is, but you can still scan and find it, right? So that's the idea of top-down design. We start with the top, okay? In terms of a map, what do you think is the top level? Keep going up, right? We keep going up and up. That's our top level. Top. Down. Top. Down. Is that okay? So once again, someone can someone remind me why we need this particular way of looking at things? Because we can only track 5 things at a time. Okay? It's our own limitation that makes this necessary. How many files do you have in a subdirectory? Well, okay, let me rephrase that question. Ideally speaking, how many files do you want in each directory folder, in each folder? Maybe 10, maybe up to 20. 20 is kind of pushing it, right? How many people have like 500 items in a single folder? Pictures, right? Yep. But that makes it kind of difficult to find the one picture that you want, doesn't it? Okay. So top down, is about short-term memory. We can only track about 5 things at a time, and it is also about it's also about how easy is it to find something. Okay. So that's top-down design, or the concept behind it, why it is important. So in programming, how do we apply that concept? Okay, we know how to use that concept in writing an English paper for English writing 300, but in programming, what do we do when we say, okay, let's apply the top-down design concept or approach to write an algorithm? How do we do that? So what we'll do is I'm going to use an example. If you have read the notes already, the rest of this lecture is going to be a little bit boring, okay, because you know exactly what I'm going to talk about and you know the algorithm already. So I'm somewhat banking on the assumption that you have not read the notes despite my recommendation. Okay, let's think about factoring. Okay, so what is factoring? So I give you a number, let's say 182, and I say, give me all the prime factors of 182. What does that mean? Go ahead.
You get all the numbers that multiply into 182.
So you get all the numbers where the product of those numbers will multiply to, the product becomes 182. And on top of that, I also want each number to be a prime number. Okay, so 2, 81, that's not quite getting the entire job done because 81 is not a prime number. Is that making any sense? Okay, so I'll just right here, okay, using my notepad, I'm going to give you a concrete example of what it means when we say factoring. Okay, so we say 182 is 2 times 81. Okay, because I can easily tell the 182 is divisible by 2. I hope nobody is surprised that we can tell the 182 is divisible by 2. Yes? Okay, very good. So now we have 2 times 81. Okay, you look at, now you focus on 81. Is 2 a prime number? Yes. Okay, so we got that done. Okay, so we can now focus on 81. So you, oh, it's 91? Oh, darn it. Okay. It's still okay. So we now look at 91, which is also an interesting number to look at because none of the tricks that we have learned works on this guy. Okay, so how do we know whether a number is a multiple of 3? What is the rule of thumb to do that? Add up all the digits of the number. If the sum of the digits is itself divisible by 3, then the number itself, the value of the number is divisible by 3. Okay, does that apply here? No, 9 plus 1 is 10. 10 itself is not divisible by 3. Darn it. Okay, how do we know a number is divisible by 5? That's an easy one. If it ends with a 5 or 0, then it's divisible by 5, right? Does it apply here? No. Maybe 91 is a prime number. Maybe not. So I think I accidentally used a very good example. Because 91 is actually a composite. It is not a prime number. So how do you know that, oh, if text says it's not a prime number, then what are the factors? What is a factor of 91? You move from, okay, so think of all the prime numbers that we have tried already. It's not 2, it's not 3, it's not 5, maybe it is 7. So you try to divide 91 by 7, and what do you get? 13 with no remainder. It is actually divisible by 7. But this is a very good example because it fails all of your rules of thumb. You actually have to test now. Okay? So you now say, okay, it is 7 times 13. Okay? The next step is to say, okay, we know 2 and 7 are prime numbers. Do we know 13 is a prime number? How do you know that? Okay, as bad as this may sound, in this class, I just know doesn't cut it. Okay, so how do we know 13 is a prime number? How do we procedurally test it? Yes? Okay, so every number is divisible by 1 and itself. The question is it divisible by anything else, right? Okay, I think that was a point, is whether it's divisible by anything else. But how do we know it is not divisible by anything else? Yes? Exactly. So you try it out, right? So you try to divide 13 by 2, has a remainder of 1. You try to divide 13 by 3, it has a remainder of 1. Can we try 4? Is it wrong to try 4? It's not wrong, okay? In other words, if you divide 13 by 4, you are guaranteed that the remainder is not 0. In other words, you cannot accidentally find that, oh, 4 is a factor of 13. So it's actually okay to test whether 4 is a factor of 13. It's just wasting time. But it won't give you the wrong answer. Is that okay? Does everybody understand or can differentiate between it is not a good idea because it is wasting time as opposed to it is not a good idea because it will give you the wrong answer? Can we differentiate between those two not so good ideas? Yes? More or less? Okay. So we divide 13 by 4 and it has a remainder of 1. So that means 13 is not divisible by 4, right? So here comes another question which I'll address maybe a little bit later. Do we need to try 5 or can I stop now and go like, okay, we're done? We can stop. Why? I mean, 5 is not even 1/2 of 13. So how can I conclusively say that 13 is not divisible by 5?
Can multiply by 2.
Huh?
Multiply by 2 is more than 13.
Nope. It has to do with we have tried 4. 4 times 4 is 16. And if 16, if the square of the number that you have tried is greater than the number in question, you can stop. Okay? That's a pretty nifty trick. Okay? I'll show you why it works. But we know that 13 is a prime number. So that means we are all done here. Okay? So this is factoring. Do we have any questions about what factoring is about? I hope not. We good? Okay. Do you think I will teach you something that is useless? I mean, you don't have to tell me. Occasionally, I might teach you something that is useless because it is interesting to me. But in this case, it is not, okay? Why do you think factoring is important in computer science? We can start with something that we know, and then we can move on to things that we do not know. We may not know. Crypto something. Okay, so you are working on something that I consider as, okay, maybe most of you do not know. So good job, you know about crypto stuff. Okay? I'm sorry? Well, you know the connection between crypto stuff and prime numbers. That's good. Okay? That by itself is a good thing. So if I have a magical box and you can give me any number, and I can immediately, like within a very short amount of time, tell you all the factors of that number, which also implies it would be able to tell whether the number is prime or not, right? It would be super duper easy to crack all kinds of encryption that is in use today. Because the encryption schemes used, the most common encryption schemes used today are all based on it is not that easy to factor huge numbers. Okay? So if I have a magical box that can factor huge numbers into its factors, I would be able to crack encryptions like that. Okay? So do you think that might be of some importance in computer science? I would think so. If you go onto Facebook and you say, "Oh, I found a really good way to factor numbers and I can crack encryptions," guess what? You might find a whole lot of black unlabeled trucks where you live. Governments of all nationality and all branches of the United States government will be interested in you because you have just found a way to crack encryption. So what is the importance of, okay, I just found a way to effectively and very quickly crack encryption. What is the significance of that? Oh, I can get onto the Wi-Fi of my neighbor now. Haha. Right? Yes, go ahead. Huh?
Military stuff?
Military stuff.
I can vouch about those encryption, those courses.
You can do all kinds of stuff, okay? Every single thing that we trust now digitally is because of encryption or cryptographic stuff, okay? If you can factor numbers really fast, you would have broken that trust entirely, okay? Across the board, nothing can be trusted anymore. Okay, do we understand the implication? So factoring by itself is a very interesting topic. Okay, people are always trying to find faster ways to find prime numbers so that you can increase the encryption strength, or they can try to find a faster way to factor a number in order to crack encryption. Okay, so something as simple as factoring is actually at the heart of encryption today. It is super duper important to computer science and computer security. Is that okay? So all of this is just to make that one point of, no, I am not teaching you something that is useless. Now we can move on. So moving on is, okay, but how do we write an algorithm to do just that? Okay, I think that's legitimate, right, as a question. So what I have just done here is not exactly using an algorithm. I'm just showing you how I do it by hand. Is that okay? So we want to do it by hand a few times, and then we can see if there's a pattern. And if there is a pattern, we can now generalize or abstract into an algorithm. Okay? So we'll try a few more examples. Okay? So we'll try 18, okay? Because 18 is pretty easy, okay? So we say, okay, we know 18 is at least divisible by 2, so we have 9 left. And then the 9 is divisible by 3, and then 3 itself is a prime number. It cannot be divided into any other prime numbers. So we're done, right? Okay, so that's not too bad. Let's try 144. You guys have to like 144 because it has a lot of factors. But many of those factors are the same. So let's try to break this down. It's 2 times 72, okay? But what is 72? It is 2 times 36. What is 36? 2 times 18. What is 18? 2 times 2 times 2, okay? 18 itself is 2 times 9. And what is 9? 2 times 2 times 2 times 2 times 3 times 3, right? What is 3? 3 is a prime number. We cannot break it down any further. Is that okay? But you can see that on each row, I'm only working with one number. On the first row, I'm working with 144. On the second row, I'm working with 72. On the third row, I'm working with 36, and so on. So I'm breaking a larger task into smaller steps now. Is that making any sense? Okay? Okay, that's kind of cool. So let's try to write an algorithm to do this. Okay? So when you write an algorithm, you have to think in terms of what tools or what vocabulary are available to you. Okay? So if you think in those terms, it's no longer like super duper wide open. It now becomes like, okay, what kind of control structure do I need? Now, how many control structures have we talked about? 3 main types. The first one is a sequence. Do this, then do this, and then do this, and then we're done. That is a sequence, which means I'm just specifying the order of getting these things done, but you have to execute everything in that specified order. There's no deviations from that order. That's a sequence. Okay? We have conditional statements. Okay? We just drew a picture of a conditional statement. So what is the biggest selling point of a conditional statement? We can make decisions. Okay? So given at a certain point, I can now say, well, I got this path and I got this path. To decide which way to go, I evaluate a Boolean expression. If the expression has a value of true, I go on this side. If it is false, I go on to the other side. It gives me the ability to choose between 2 alternative paths, right? And then after I have chosen one particular path and executed that path, what happens to a conditional statement after I have followed a particular path? You have to get out of the conditional statement. You're done. In other words, it's a one-shot deal. Okay? Okay. What about the third type of control structure? It's called a loop, right? So what does a loop bias? Why is it important? What can it do that the other 2 cannot do? Yep. To keep us in? I think what you're trying to say is we can do the same thing over and over again. Okay? Repetition. Okay? Yes, so that's something that we can do with repetition. So now the idea is you look at how we factor 3 different numbers. So now you have the question. The question is, do we want a sequence? Which means, okay, A, B, C, D, but we can only apply those steps in that particular order to every single input that we get. Okay? That's a sequence. Or do you think we need a conditional statement where we can say, well, we can kind of decide between these 2 paths, and then each one can have its own decision and so on. But at the overall highest level, we can just say, okay, go this way or go that way. Okay? Or do you think this reminds you of, Tag, this is boring. Are we done? Because that means there's repetition. Right? So which way do you want, which one do we want to choose? Sequence, conditional statement, or loop? I think a loop makes sense, right? Don't you think we are kind of being a little bit repetitive here? I chose that example because it is very repetitive. It looks very repetitive, okay? All right, so let's try to write the algorithm then. So we say, okay, loop and loop, exit when, blah, 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 okay? In other words, I am going to start writing the algorithm in even a language that is not in pseudocode. I never talked about loop and loop in pseudocode. Well, I cannot choose between a while or repeat until later. So all I'm trying to express here is to say that, yeah, we have some kind of a loop, but I don't know whether it's a repeat until or while loop. I just know that we have repetition. But whenever you have repetition, you kind of have to know, so when are we going to get out? Right? Because otherwise you have an endless loop. There are very few cases where an endless loop actually makes sense, but in most cases, we do not want, we don't want endless loops. We want loops that can get out, okay? So we automatically have two additional questions now to answer. One question is, what are we doing inside the loop here? And then the second question is, when do we get out? When are we going to get out of the loop? Okay? So you look at the example that we have, it's actually easier to figure out when we can get out. Okay? But we need some kind of vocabulary to support that. But let's just say that we don't want to go that far yet first. So how would you describe this process or the process before that? When can we get out? How would you describe the condition to get out of this repetitive action? I'll let you guys, I'll let you guys specify it. It can be just plain English. Doesn't have to make use of variables and. Sorry? When the number we need to factor is prime. Okay, very good. Okay, so let's do that. So we'll just write down when the number to factor is prime. Okay, very good. Guess what? Congratulations. We got version 1 of our program. Is it going to work? Is it going to compile? Is it going to run on the computer? Absolutely not, okay? But it does capture something that's important, okay? It does capture the fact that, maybe it is important for me to see if something is prime or not, okay? So can we use a variable name to replace the number to factor? Because, that seems pretty long as a name. Yes? Okay, so we can use x, we can use n. Okay, let's pick x. Okay, so this is version 2. So version 2 says x is the number to factor. So this way I don't have to write a whole lot of stuff, right? So now we can get back here and say when x is prime. Yay! Cool. But in addition to just replacing the number to factor as x, okay, which is great because we don't have to write the same thing over and over again, we might want to look at the process and say, how is x changing over time, right? Because x starts off with, in this particular example, as 144, right? Because that was the number given to us to factor. How did it get from 144 to 72, and then 72 becomes the number that we want to factor? It became 36, 36 became 18, 18 became 9, 9 became 3, and then 3 is prime, and we're done. So how did we move from one value to another value? X obviously has to change as we execute the loop, right? So how did it get changed? Are we dividing by 2 for every single case? What is the 2 representing? How is that 2 relating to x? Yes, go ahead. It's a prime factor. Okay, so it sounds like, in each step that we have observed here, there's one thing we need to do. It sounds like we have to find a prime factor of x in each iteration. Does that make sense to you? Because, on the first line here, we found that 2 is a prime factor of 144. Going from here to here, we found that 2 is a prime factor of 72. From here to here, we found that 2 is a prime factor of 36. From here to here, we found that 2 is a prime factor of 18. From here to here, we found that 3 is a factor of 9. So that means in each iteration, we have to find a prime factor of x. Yes?
How do we change the assignment of x from 144 to 72 in a program?
In a program? Well, we'll figure that out. So we'll worry about how to express it later, but we want to capture what it needs to do first, okay? So I think we agree that we need to find a prime factor of x. Yes? Sounds like what we need to do. And then what do we do to x itself for each iteration? In other words, how do we go from 144 to 72 once we found out that 2 is a prime factor of 144? What just happened? Not mod, but pretty close. Divide, okay? Divide, we just need a quotient, okay? We just need a quotient. So we say that it sounds like for each iteration we're doing something like this. X gets x divided by, the previously found factor of x. Okay? If you are a lawyer, you probably want to say said found factor of x. Okay, no one here reads a lot of legalese. Okay, never mind. It's okay. Well, all this is saying is this part here is whatever we found here. Is that okay? That sounds really confusing. And a lot of typing. Yes? So maybe if we give that found factor, prime factor of x, a name, we can make this more clear. We can clear this up a little bit, okay? But you know what? I'm lazy. I'll call this version 2. And now we can enhance this program as version 3. So this way, in case my boss asks me, Tech, what did you do today? I can say, oh, we worked on like 4 different versions of this program. So in version 3, what we're going to do is we're introducing a new variable. Find a prime factor f of x. In other words, I am calling the factor of x f. You can choose other names if you want to, but since factor starts with f, I just want to stick with that. Is that okay? How would that impact the next line? Now that the factor has a name, do we want to refer to it? Yep.
Divide x by f.
Yep. Exactly. Okay. Cool. Ooh. Okay. I have one little problem with exit loop, end loop exit when x is prime. What do you think is the other thing we can do to get out? In other words, if we keep doing it like this, what do you think x eventually will get down to? Sorry? 1. Very good. Good job. X eventually will get down to 1. And, okay, here's a little question for you guys. Is 1 a prime number?
No.
It is not. Very good. X is not a prime number. And you ask, why? But 1 is divisible by 1 and itself, so it meets that requirement. No, it is not a prime number because it is by definition not a prime number. If you look up the definition of what is a prime number, it says 1 is excluded. Okay, 1 is not a prime number. Okay? So that's kind of besides the point, because I can say when x is 1, we are done. Because we don't have anything else to process. Would that work? So are we agreeing that we can change the exit condition to x equals to 1? Because by the time x equals to 1, that means we have already found all the factors of the original value. Yes?
So in a program, you couldn't just say when x equals like multiple, you couldn't have like multiple like scenarios, so you couldn't put all the prime numbers there?
You can only find 1 at a time. So because remember, the computer is kind of dumb, okay? It can only do one type of calculation at a particular time. So when you say, okay, find me a factor, it can find you a factor at a time. It's not going to come back and say, oh, you know what, 18 is 2, 3, 3. Nope, it will just say, oh, you want me to find a prime factor of 18? 2 is one of those. Then you have to ask again and say, what about 9? Oh, 9 has a prime factor of 3. Then you have to ask again, and what about 3 itself? Oh, 3 is its own prime factor. So now x eventually gets down to 0. Are we doing okay so far with this code? Yes? Sort of? Okay? All right. So this is version 3. And now I'm going to work on version 4 because I want to get this program or this pseudocode to the point that we can actually run it. Okay? So in order to move from version 3 to version 4, my question is, do we use a while loop or do we use a repeat until loop? That's the question. In other words, do we check the condition first before going in and say, oh, let's find a factor for x and then we change x to a smaller number, or do we just do that first and then we ask, can we get out now? So it depends on one thing. It depends on what assumptions can you make about the first value of x. Okay? If somebody can say, oh, tech, this is a value of 1, go factor it. Then I have to use a pre-checking loop because I have to get out right away because 1 has no factor. It's not even a prime number. Okay? On the other hand, if somebody says, oh, the initial value of x is guaranteed to be an integer that is greater than or equal to 2, then a repeat until loop is okay. I can actually do that. Is that okay? But in this case, the while loop is the more general solution, so we'll go ahead and convert it into a while loop. So when we convert something into a while loop, okay, we still have x is the number to factor, it's a given number, but then we have the while do and while, and then in between we have the same stuff, okay, which is find a prime factor f of x, x gets x divided by f. So now the question is, what condition do we specify here? Remember, in a while loop, we are specifying the condition to stay in the loop. We are not specifying the condition to get out of the loop. Is that okay? Yes?
Is it x is larger or equal to 2?
X is greater than 1 would work, or greater than or equal to 2 would work as well. Okay, so we have to flip the condition, and now we specify as long as x is greater than 1, we got something to do. Does that make sense? Because when x is 1, we can get out. So if you look at it the opposite way, it also means that when x is greater than 1, we got work to do. Is that okay? So it sounds like we are refining the algorithm step by step to the point where, I think we got it, okay? So let's go ahead and track this one down and see if we can run it. So we'll give it some line numbers, okay? So this is the first line. I'll make this pre, by the way. We'll make this pre because we're basically just saying that give me a number to factor, okay? So that will make this the first line, the second line, the third line, and here's the fourth line, okay? And after that is post, but that doesn't need to be specified. So I'm going to use this spreadsheet, to work on this. All right, so this is the trace, okay? So sheet 6 of the spreadsheet is now the trace of the algorithm. We have comments, we have line number, and we got 2 variables this time. We got x and f. This is the precondition, and the precondition says, give me a number to factor. Okay, so what do you guys want to do with this number to factor? You can choose one of the numbers we have worked with already, or choose some other numbers. I don't really care. Huh? Sorry? Say that one more time. 10,955. Okay. 10,955. Okay. That's okay. Not a problem. So we move on to line 1. It asks the question, is x greater than 1? What do you think? True, okay. And I just need to find a prime factor of 10,955. Which one seems kind of obvious to you? 5, okay. So 5 is stored in variable f, okay. So on line 2, f gets 5. And then on line 3, what do we get? This is where, I get super duper lazy. Okay, I mistyped something. Equals that divided by that. How lazy can I get, right? Okay, but do you guys see what happens after one iteration? I magically found one factor of the number, and then I say, okay, since this is one factor, let's find out what else do we need to do with this number by dividing the found factor, by dividing the number to factor by the factor that we just found. Okay, so this is what line 3 is going to do. Where do we go from here? Yes. Yeah.
So wouldn't we have to change like the value of f every time because 5 doesn't go into?
Yeah. We have to find another prime factor potentially for each iteration. Okay. So, but focusing on line 3. Okay. Where do we go after line 3 is done? We go back to line 1 because we have to go back to the beginning and say, are we done? No, not even close. Then we go back to line 2 and we look at 2,191. And it's definitely not divisible by 3, right? Okay. So we can just say, okay, magically we can try to factor this, okay? Which means I'm going to, as a lazy person, as the original algorithm, I'm going to subcontract to you and go like, hey, find me a prime factor for 2,191, okay? And then let's step back and then wait. Yep. 7? Okay. So we'll try 7 out. Okay, so we'll say 7 is here. I'm assuming that you checked already. Okay, so you got a trick to do. Okay. So now the new value is the old value divided by the new found factor. And you are correct. It is, in fact, divisible by 7. Good job. Okay. And then we go back to line 1, and we ask x is greater than 1. It's still true. Go to line 2. So now we have the factor 313. 7 is not going to do, right? Because if it's 7, then you have 28. Then we have 33 left. Okay, what about 11? It doesn't look like it's divisible by, it doesn't look like it's divisible by 11 at all. Let's try 13, okay? So 13, we have 2, 13, 60, 26. So we have 53, which is a prime number itself. Doesn't work, okay? 13 doesn't work. 17. 117 with 14, 143 divided by 17 is what? 140. Okay, I'm just going to be super duper lazy here. And then we say factors of 313. It is a prime number. Okay, well, if it is a prime number, there's still an answer to that question because on line 2, the computer is told to find a prime factor f of x, right? X is 313, and what is a prime factor of 313? Itself, okay? Because every prime number is a prime factor of itself, okay? So we just say, okay, we just found a prime factor, and then we go to line 3, and then say, okay, the new value of x is its current value divided by the factor that we just found, and it is 1. Can we say post now? Yeah. No. Why not? Yep, exactly. We have to go back to line 1, which is the only place we make a decision in this particular pseudocode. Now we can say post. Is that okay? Is that cool? Okay. So it's 33, we are about 15 minutes away from the end of the class, of the lecture. And I haven't mentioned a single thing about top-down design, did I? Right? But I did. Remember I said, I'm going to subcontract that task to you, right? Here's 313, go find the prime factor for me. That is top-down design. In other words, procrastination and laziness sometimes can accidentally lead to good top-down design. Okay, no one is... Do you guys understand what I just said? Okay, what do lazy people do? Like me, I just said, this is like kind of a lot of work. Why don't you do it? That is top-down design, because I'm leaving the details of a task to somebody else so that I can focus on the overall logic of factoring a number. I'm basically delegating the job of finding a prime factor for a particular number to a separate piece of logic so that I don't have to specify here, I don't have to keep track of more than 5 things at a time. I can keep this logic clean and simple. Is that okay? So are you guys understanding why this example is already illustrating top-down design? Yes? Okay? Well, top-down design, unlike, doesn't mean that you don't have to do it. As I said, it is procrastination. You still have to do it, just later. Okay? So now I have a problem. It's like, oh, you bounce me back to me and go like, Tack, I really don't know. You are the teacher here, so I don't know how to find a prime factor for a given number. I go like, okay, do we have to do it? Yes, we have to do it. So now we say, okay, we have a sub-problem. But the sub-problem is very contained, because the sub-problem is simply saying, okay, Tack, here's a number x. Find a prime factor for that number. That's all I need to do now. I don't have to keep track of, we're trying to reduce a number down to, its components, okay? We're just finding one single prime factor at this time, okay? So now the question is, well, is that an easy thing to do, or is it a really hard thing to do? And if it is a hard thing to do, how do we specify the logic to do it, okay? So I will give you some simple examples first, and then you tell me, so let me say that this is x, okay? And if it is 14, what do you think is a prime factor of 14? You guys know it's 2, right? Because we got a rule of thumb, if a base 10 number ends with 0, 2, 4, 6, 8, it is a even number. And all even numbers are divisible by 2. That's pretty easy, right? Remember the other one that we worked with, which is 91? And I said, okay, give me a prime factor of 91. And we kind of hesitated. We kind of slowed down there and go like, all the tricks that we know, don't work anymore, right? It is not obviously, well, okay, I should say the other way around. It is obviously not divisible by 2. Okay, it's not divisible by 3. It's not divisible by 5. Is it obvious that it is divisible by 7? Nope. There's no easy way to tell that 91 is actually divisible by 7. We actually have to try to do it. Yes? So as if that is not enough, we now have 313. How do we know 313 is a prime number if we are not going to look it up on using Google? You have to try it, right? So you have to try, okay, as dumb as it seems, we try first with 2. Okay, 313 divided by 2 has a remainder that is non-zero, not divisible by 2. Move on to what? 3. And I said already it's okay to try 4, even though 2 failed already, 4 is guaranteed to fail, but it's okay to try it. The reason why we try 4 is because it is kind of cumbersome to have to keep track of a list of prime numbers. It is a whole lot easier just to move on to the next available integer. Okay, so we'll try 4, nope, doesn't work. We'll try 5, nope, doesn't work. We'll try 6. But tech, it didn't work with 2 nor 3, 6 is going to fail. It's okay, let it fail, because it saves me the trouble of having to keep track of a list of prime numbers. Okay, we'll try 7, doesn't work. So we keep going and going and going. The question is, when do we stop? Okay. So using a spreadsheet, I can tell you, the whole process. Okay. So F is going to be here. Okay. These are the potential Fs. Okay. And on this column, I'm going to say F mod X mod F, which is basically the remainder of X divided by F. Okay. I can just spell out that way too, but it's just the remainder. All right. So this looks, okay, so we will start with 2. We cannot start with 1. And in the case of 2, X mod F is going to be the mod of this number divided by that number. That seems pretty good, right? But I have to do one little trick here. I have to make a $sign of this 1 so that I can use another trick later on. The next number that I want to try is just 1 more than the previous number, right? 3. So we say, okay, it is whatever we have before plus 1. And you guys might think, Tech, that's a lot of keystrokes instead of just typing 3. You would be right about that. But I do this for a reason, okay? And then with the other one, this is a spreadsheet trick. You can use this to copy a formula. In other words, if you look at this formula and you look at this formula, they are almost exactly the same, with the only difference of this one is referencing C2 and this one is referencing C3. And it's automatically done. Do you see how this can be quite useful? Because now I can select these 2 cells and drag it or just kind of replicate it like so. Okay, kind of cool, right? And I want to keep track of something else too. I want to keep track of the square of F. Okay, so square of F is pretty easy to track. Okay, it's really just this number times itself. So I want to track that. And I don't have to go very far. So I can't stop now because even at this point I cannot conclude that 313 is a prime number. So I keep going a little bit more, and at this point I can stop. I don't even need this row here. I can delete that. So by the time I can tell that 18 squared is 324, and the remainder of 313 divided by 18 is 7, I can stop. At this point, I have just confirmed that 313 is a prime number. Are you guys convinced that I can stop at this point? Yes?
Oh, but what if say you said this has a lot to do with the encryption, right? But what if the number isn't 313? What if it's like 1,407,000? Would you just keep looking down the list until it is?
No, there are much more efficient ways to find a factor, but we are only concerned about the basic ways first, and then we can potentially look into the more advanced ways. Yes? If I don't put a $sign, that particular cell reference would also move with what cell I copy it into. By putting a $sign there, I'm basically saying this one stays put. Do not move this one along as I copy the cell to other cells. Okay. So these are spreadsheet tricks that you can learn in the spreadsheet class or on your own. Okay, because these are really quite useful tools. So the question is, why can't I stop now? So one thing you can do is to say, okay, let me just kind of look at all the prime numbers that I know, okay, and see if this approach works. Okay, I will try to find a factor up until about the square root of the number. If I cannot find any, is that true that any number that fails that test is going to be a prime number? Okay, and you will find that the answer is yes. Okay, it is true for everything. So what are you going to do? Well, there are 2 things we need to do now. One is to code this into pseudocode. The second one is to prove that this is actually a good time to stop. We don't have to test all the way to even 1/2 of the value that we need to factor. So let's focus on one thing at a time. Okay, the one thing that we focus first is, okay, how do we turn this into an algorithm? Because after all, that is the focus of this class. So let me see if I can, we can do that. Okay. Okay, so now our focus is to find factor f of x. Okay, the question is, what do we do? Looking at the spreadsheet, does it look like a sequence? Does it look like we can do one thing, like it's a one-shot deal, we're done? Or do you think it involves repetition? Do this, nope, doesn't work. Do this, nope, doesn't work. Do this, nope, doesn't work. Keep doing it until, okay, now we can get out. Which one does it look like to you? Repetition, okay? So with a repetition, just like before, we say loop and loop, okay? Loop, blah, 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 and loop. And we can say exit when, blah, 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 okay? So we focus on the condition to get out first, okay? Under what condition are we getting out in this case? I mean, the square of f is greater than the number that we're given with. That's one way to get out. Is that right? Okay, so we can specify that condition. So we say when f times f is greater than x, we can get out. But wait, tech, we can only get out this way because the number itself is prime. What if we're given a number that is not prime? Okay, so let's work with a number that is not prime. Let's say 315, okay? So when you look at this table, when do you think we should get out of the loop? When f is, okay, this column is f. So when f is 2, obviously we cannot get out. But when f is 3, we can get out. Why are we getting out when f is 3? Because what is 0? X mod f is 0. Does it make sense? No. Okay. So in this particular example, when x is 315, okay, when f is 2, we cannot get out because we have neither found a factor nor confirmed that x is prime. Is that okay? My job is not done yet. Okay. When f is 3, then we found that the remainder of x divided by f is 0. What is that telling you? What is it telling you when x divided by f has a remainder that is 0? It is a factor, right? F is a factor of x. Wasn't that my job? Is to find a prime factor f of x? Yes? So I'm done. So that means here when f mod f, which is the remainder of x divided by f, is 0, I can get out. I have found the factor. Is that okay? Okay, so how do we incorporate this into this logic here? Because now it looks like we have two conditions to get out, right? So when x mod f equals to 0, that's a reason to get out as well. When you have two values that are both Boolean and you have to combine them into one single Boolean value, what are you going to do? What are my choices here? What can we put as an operator between these two? Oh, okay. Does anyone want to, and, okay. Or, okay. So we can use, this is a place where and can go, but or can go here as well. So now we have to ask the question, which one do we want? We want an or, because both of these are good reasons to get out of the loop. So we want an or, so that if at least one of these two conditions is true, time to get out. Is that okay? So you can, we may not have enough time to finish the whole thing, but you can see how when I try to approach to write an algorithm, I focus on what kind of construct is it. Is it a sequence? Is it a conditional statement? Or is it a loop? Most of the time, it is a loop. Okay, you're doing something repetitively. Once you identify that you have to do something repetitively, the next question that I usually ask is, when do I get out of the loop? Okay, I know we are running out of time. We still got 2 minutes, so I can still continue to yak for 2 more minutes. So when the condition, involved in determining when to get out has mentioning of x and f, okay, then the next question you have to ask is, which one or which ones am I going to change so that we can eventually get out? Does that make sense to you that at least one of these two has to change? Because if they don't change and initially this condition is false, then it becomes an infinite loop. You will never get out. So the only reason why you can get out is because you're changing at least one of these two. So now the question is, am I going to change the problem given to me? Like somebody told me and go like, Tech, go find the prime factor of 25. The answer is, oh, I know that 2 is a factor of 4. Would that be acceptable? No, I cannot change the question, right? So that means x cannot change. And you can tell from the spreadsheet that x does not change either. I kept using the same x, right? So if x is not changing, which variable has to change in order to exit eventually? F has to change, okay? And I know we only got 1 minute left, but that's all we need. What am I doing to f for each iteration? Increase by 1 for each iteration. So that means over here, for each iteration, this is what I'm doing. That's it, okay? And we still got some seconds left. I don't know exactly how many. And by the time I know how many, it's already too late, right? Oh, over by 2 seconds too. Okay, never mind. So next time, we're going to convert this into actual pseudocode that we can trace, okay? All right. I'll see you guys next Tuesday when we have our exam 1.